Welcome back, CHEM200 to Chapter 10, Part 2. Again, homework is out there. If you want to talk about homework, exam, please see me during office hours. Quiz 6 is coming up, May 18th, last quiz. Exam 4, May 20th. I don't know the cutoff when they can send this study guide, so if you want it, you need to double check with them and get that ordered as soon as possible. Review sheets posted for the exam. So if you take a look, this is Chapter 10, Part 2. There is one more new material lecture after this, one more quiz, one more lecture exam, and then it's the final. So if I can't emphasize enough, you know what's coming. Finish strong, people. The end is near, so let's deal with all the adversity that's happened this semester and give it your best. I think it'll make a difference here at the end. So we spent quite a bit of time on the previous video in this chapter looking at equations, calculations for gases. Really now we're going to start out with quite a bit of theory, so the explanation for this, and then we're going to end with some of it as well with some equations in between. So the kinetic molecular theory is a very common gas theory. Maybe you saw it in Chem 152, size of particles very, very small. So you can see mostly empty space in a gas. The average kinetic energy of those particles is proportional to the temperature in Kelvin. I can't stress this, circle it, star it, whatever, enough. If you're in gases, you need to convert to Kelvin. And the collisions are elastic, so energy isn't lost. Okay, so this is pressure. This is where pressure comes from. It's the collisions. So if we're on campus, this would actually be your time to discuss this. What I mean by that is I'd say this is Boyle's law. There's a difference in pressure. Okay, there's a difference in volume. Explain. That's the whole point of these next few slides are what's the explanation. Okay, so for Boyle's law, remember this all relates to the ideal gas law. PV equals nRT, and in this case the nRT is constant. So we need to think about if we increase the pressure, so that's one weight to 2, okay, what's happening? Okay, so if we take a look here, the volume is decreased. That's the answer. It says it right there. No, the question is why? Why is this the case? So the key is the amounts are the same. Okay, so the amount of gas particles over here are the same. Check. Okay, so the temperature is what the kinetic molecular theory is, the average kinetic energy of those particles to remain the same. So the pressure, so the collisions here and the collisions here, the volume has to be altered to remain that same. So I actually have a simulation. You can put in different gas conditions. If you're interested in that, let me know, because then you can take a look at it and adjust it yourself. What if I increase the pressure? What happens to the volume? What if I increase the volume? What happens to the pressure? So this is this relationship. So Charles, okay, what if the temperature is increased? Okay, so then again, this is ideal gas law. And what we can see is that the pressure is constant. Okay, so this is V over T. So if we're doing two conditions, which we've got here, V1 over T1 equals V2 over T2. That's the rearrangement of the variables. The others are all constant. Okay, so what we're seeing here in Charles' law, if you increase the temperature, the gas particles are moving faster. So to remain the same pressure, 2 weights and 2 weights, you have to have a greater volume so they're not colliding as much. Okay, so that's the description. Kinetic molecular theory, temperature increases the kinetic energy, so we need more space, so then the pressure remains constant. That means that volume and temperature are directly proportional. So volume increase, temperature is increased. Avogadro's, you can see if we're again keeping the pressure constant, 1, 1, so this is PV equals nRT. That should be the go-to right away. Any kind of theory question, any kind of calculation question, you want to go to this and see what's constant. Okay, so this is volume in moles. So that's V1 over N1 equals V2 over N2. So if we've got this, we can see that, again, if we're putting more, so there's some gas, we're putting more gas, we're putting more gas. If the pressure is going to remain the same, the volume's got to increase. So these are directly proportional as well. So the collisions to remain, for the collisions to remain the same, we've got to have greater volume if we have more stuff, if we have more particles inside. Even Dalton's partial pressure law applies. So if this is a certain pressure, and then our red is another pressure, these are additive. You put them together, and you can add them up, and that was our calculation on last video. So that's the theory explaining our laws. So let's look at a couple of other pieces, and this is the molecular velocity. So there's a lot of ways you can look at velocity, but the specific one here is the root mean square velocity. So this is this equation, square root 3RT over m, root mean square, and you might see a calculation with this, might not. That's not really the focus for me on this slide. The focus is, look at this, oxygen and hydrogen. Those are the two extremes we're going to look at. Okay, and if you look on the y, that's the relative number of molecules, and this is the speed, the velocity of the gas. So this is actually a real challenge, and when we're doing this in class, this happens a lot. It can be really confusing, because if you look, this is the highest peak. So if my question is which gas is the fastest, a lot of people will say it's oxygen. Okay, what we need to look at is our axis. Remember, the speed is on the x-axis, so really hydrogen is the fastest gas. Okay, oxygen is the slowest gas. But then take a look. So speed, you can see then the size matters. This is oxygen, it's the heaviest, slowest, and it goes on and on. The smallest is the fastest. But the number of particles, you see how thin this line is the heaviest. Okay, look how hydrogen is the lightest, and it's spread out. Okay, so these are the takeaways. Lighter particles travel faster, and on average than heavier ones, and they have a greater distribution. So that's the distribution, what we're looking at here. So now let's take a look at just our nitrogen here, but this is at different temperatures. Okay, so you can see, again, we're not looking at the y-axis, that's the relative number when we ask the question, which is the higher velocity, which is the faster. Okay, so of course the higher temperature has the fastest distribution, or has the fastest peak over here. Then lower temperature, lower speed, lower temperature, even lower speed, but for sure you heat it up and it spreads out more, just like that light hydrogen gas from the graph before. So higher temperature results in higher average velocities. So this slide here I think is always an interesting one. This is called the typical gas molecule path. This is called the mean free path. I've also heard it talked about as like a bargain shopper. You can imagine if you're walking, if you shop anymore, if you're walking, you see a deal, Black Friday shopping, you see a deal, and then you walk straight directly to the next deal. And then wait a minute, you see another deal, and you walk over there. So this is the path between your deals. Oh, what about that one? That's a good deal, okay? That's called the mean free path for gases. So the average distance between collisions, okay? So now if we talk about two gases coming together, okay? So this is a diffusion This is a process where the gas spreads out because of the concentration gradient. And if we have ammonia gas on the left and we have hydrochloric acid, which goes to HCl gas, and you can see that they diffuse. And look at the paths, the mean free path or the bargain hunter path. They're not in direct straight line running for the end or anything, but this is the path that they take, the collisions, and then get there. Now let's take a look at where they actually mix and form the product. Okay, we've got this distance that was traveled by ammonia, and we have this distance that was traveled by HCl. That's what the previous slides are leading us to. The mass affects the speed. So ammonia, NH3, 17 grams per mole roughly, that is a lot lighter, can go faster than hydrochloric acid goes into HCl gas. That's 36.5 grams per mole. So very different diffusion process. So I really want to emphasize here that this is diffusion. Okay, concentration gradient spreading out. Well, this one is a fusion. Okay, so a fusion is going through a small hole, but it also depends on speed. Okay, so heavier molecules fuse more slowly than lighter ones. As you imagine, lighter ones are traveling faster, they're more likely to go into the open hole and come out. So that's a fusion. This one, it helps that there's an equation, gas law equation for a fusion, gas A, gas B, and look, they're inverse. A, B, so it's the square root of the molar mass, capital M's the molar mass, and it's a ratio. And what can throw people off is just how the question is worded. Okay, so this question is calculate the ratio of a fusion from oxygen to hydrogen. So oxygen's on top and hydrogen's on bottom. That's what it means, oxygen to hydrogen. The question could have easily been hydrogen to oxygen. But take that equation and solve, see what you get for this ratio. So if you take a look here, it's molar mass, it's square root, so it's kind of a unique equation, but they're inverse. But you got those numbers, you put them in, it's pretty straightforward. This really is the problem though. Okay, what does this number mean? This number means that oxygen is slower than hydrogen. And if we said instead, what was the ratio of hydrogen to oxygen? It's 4 to 1. Okay, 0.25 is the same thing as saying 1 to 4. So this equals 1 to 4, roughly, and this equals 4 to 1. So I really believe this calculation isn't the problem, it's usually the interpretation of the question. What does it mean? What's the rate? In this case, you could have also said hydrogen is 4 times faster than oxygen. Might have been a multiple choice answer, for example. So that's a fusion. So the next and last set of calculations are stoichiometry. Okay, so again, we've been doing so much stoichiometry, grams, moles, particles. That's no problem. And stoichiometry piece is going to something else, grams, moles, particles. Okay, so that's the roadmap that you have. And we added solutions. That was molarity. Now we're adding gas laws. That's PV and T gets us to moles. And that could take us to solutions, molarity. That could take us to gases, PVT, or that could take us to STP. So this is the stoichiometry roadmap now. You've added so many pieces in doing all this. Remember, it still goes mole through mole. You could just have a variety of ways now to get in moles, whether it's grams, molarity, gas laws, STP, you can do it. So take a look at this quick check. You've got hydrogen, 300K, 2.3 atmosphere is produced when 23 grams of aluminum reacts with hydrochloric acid. So you're looking for volume of a gas, and you're given temperature, pressure, and you're given grams of something else. So stoichiometry, you're in one thing, you need to go to something else. That should be the red flag. So go ahead, pause, take a look at this one. A couple of things you should take away from this is I need a balanced chemical equation. Okay, so aluminum plus hydrochloric acid, that gets you aluminum chloride and hydrogen. If you've got that, then you can use your molar mass to get to moles of aluminum. If you got moles of aluminum, you can get to moles of hydrogen from the mole-mole ratio. And then if you got moles of hydrogen, then it's an ideal gas law problem. PV equals nRT, R is provided, solve for volume. So that's the calculations for chapter 10. There's a few more slides that I want to touch on, and I'm emphasizing these are the calculations. We're finishing up with theory. Okay, so you can see here is that STP mentioned this 22.4. And look at this. These are looking good. 22.4, 22.4, 22.4, all looking good, except, whoops. Okay, so this is the piece of real gases. Not all gases act ideal, and this is where you're going to see the point of that. What's the difference between a real gas and an ideal gas to account for these differences here? This lower 22.06 for chlorine, 22.3 for carbon dioxide. So if we look at a plot, this is molar volume on the y-axis and pressure on the x-axis. And what I want to point out is at a high pressure, volume is higher than predicted. Okay, so remember I tried to emphasize that pressure also can be thought of as amount. So if I just make a gas with a little bit of pressure in here versus a gas with a lot of pressure. Remember, amount is there's more particles, that means more collisions, that's a higher pressure. Okay, so if we look at this then, the volume is higher than predicted. The reason is, remember we look at this scenario 1 and say that the volume is mostly empty space. Well, now if we have high pressures, so if we have a lot of particles in there, then it's not mostly empty space. There are more collisions than expected. The volume of the particles do matter now. So then if you look down here, high pressure, 1000 ATM, you can see that argon is higher than what an ideal gas. So ideal gas should be here, and argon is higher. Okay, so that differs from ideal. Well, we can also see this example at low temperature, pressure is lower than predicted. Okay, so again, our axes, we want to look at that. That's pressure on the y this time, temperature on the x. And in this case, it's all about the intermolecular forces. Okay, so intermolecular forces is the attraction of particles to one another. So if the particles have slowed down, okay, if the particles slow down, then now there can be a greater attraction when the collision happens. You can imagine a very slow fist coming together, boom, the collision, they stick together, there's attraction, versus if it's a really quick, boom, now the fists are separated. So in this case, low temperature, the particles are attracted to each other, so xenon particles are more attracted to each other, so that means the pressure is lower than the ideal. Red's the ideal, green's the xenon, and because the xenon particles are attracted to each other, they're not hitting the walls as much as expected. So what do chemists do when they have glitches like this, right? You look at this, it's a little bit of an issue there. Oh, there's modifications, okay? So this looks really complicated, but remember, our gas law is PV equals nRT. So this is the same, no problem. what we have here is a modification of the volume. We said the volume is different than expected, so you do a factor to adjust for that. This is a modification of the pressure. You can adjust for that factor. Everything else you know. So this is pressure, moles, volume times. That's our volume that we're adjusting. This is moles. The only things that stand out here are B and A, and that's the modification. They're constants. So you go to a table, you look up, there's A, there's B, it depends on what gas you have. You plug it into that equation, and now you can do a calculation based on the real gas, and it's not just the ideal. So that's a good lesson for all of us, right? Not everything is perfect and ideal. This is the one right across here, ideal. This is the reality, all these others here. So if you got questions, come see me during office hours.